core, which is higher. This is the absolute variation. This is the relative. So the relative variation is of the order of typical range is between 0.2% and 0.5%. So a very, very small variation. In this variation, it is possible to solve the Helmholtz equation in the approximation of weak guidance and obtaining the LP modes. Okay. LP modes are a quasi transverse electromagnetic solution. The only transverse electric and magnetic solution, the only rigorous term solution is the infinite plane wave. But in the weak guidance condition, all the modes of the optical fibers are nearly or quasi TEM. That is, the longitudinal component of the electrical field, this is the axis of the fiber, so the propagation of the light is along the axis, and this component can be neglected because typically is much lower than the transverse component of the electrical field along the X and the Y axis, which are transverse to the axis, to the propagation of the light. So we can consider this longitudinal component or axial component equal to 0. Okay, so we have two possibilities in terms of orthogonal linear polarization. We can have an horizontally polarized LP mode, that is, the electrical field oscillates in the X direction. So this is the so-called horizontal state of polarization. Okay, and we can write the field in this case in abbreviated form. This is the H capital state, and so the Z component is a 0, so the only component are the transverse component, EX and EY. But in the horizontal case, the electrical field oscillates along the x-axis, so the y component is exactly 0. Otherwise, the x component, it is better to use the cylindrical coordinates. So this is rho. In some text you have also r, but for the cylindrical set of reference it is more common the Greek letter rho. You can use also r. Rho is the radial coordinate. that is, if you consider a transverse plane, this is the standard Cartesian reference for the transverse plane, and the z-axis, the fiber axis, is this one, coming out from the dashboard. So, a generic point P of coordinates x and y can be also represented by the coordinates, the polar coordinates, rho, the radial coordinate, and theta, the azimuthal or angular. This is the azimuthal or angular is synonymous coordinate, where rho is the radius, that is the distance from the generic point P and the origin, which is along the axis, and theta is the angle of this radius with respect to the horizontal axis. The positive sign of theta corresponds to an anti-clockwise handedness. So in this case, this angle is positive. Otherwise, for a point, for example, P first here, this angle is negative because the rotation from moving the horizontal reference axis onto the radial segment is clockwise. So clockwise is negative and anti-clockwise is positive. Okay. And z is the usual coordinates along the axis, along the propagation. Okay. This field is expressed as a radial function. Radial means that this function is the radial part of the field because it depends only on the rho, only on the radial coordinates. But this function is characteristic of the mode. So because the LP modes are classified by using two indices, L and mu, and different LP modes with different indices will have different radial distribution. For the step index, this radial function are the bezel in the core or the ankle in the cladding, for example. For the graded parabolic fibers, this radial function is the Lager-Gauss function. Okay, but this is a general scheme for the LP modes. Actually, there is an azimuthal part that is a term of the field depending just on theta. And the standard classification of the LP modes consider as azimuthal part either a cosine or a sine. So for L, this is the angular index, azimuthal or angular index. In general, L is 0, 1, 2, etc. Okay, for L equal to 0, this function is just 1. is a particular case. But in general, for L greater than 0, you have to consider a cosine with argument L theta. And finally, there is the term of for the phase of accumulated into the propagation, which is the standard exponential with argument minus I, the imaginary unit. For a plane wave, we will have the wave number k by z. In optical fiber, you will have the propagation constant beta, which depends, because different LP modes have different beta, so beta depends on the indices L and mu. This is the phase term accumulated during the propagation along the axis, along the fiber. Okay, this term is missing in the file. I will correct and I will upload a new corrected version. So this LP modes is the horizontally polarized because EY is 0, and it is the LP modes of the cosine type, because we are using an azimuthal term with a cosine function. Cosine can be abbreviated by the A type. So it is H horizontal of the A type, that is cosine in the azimuthal term. There is also, for L not 0, we will see, there is also the other kind of LP modes, that is an LP mode, again, horizontally polarized, but with azimuthal term of the orthogonal trigonometric function, that is the sine function. This pattern is also named the B pattern. B stays for using the sine. The expression is the same, is similar. So the radial part for the same L and mu indices is the same, exactly the same function. The only difference is the azimuthal term. And y, the component y, is 0 for horizontal polarization. Okay. When L is equal to 0, as in the fundamental mode, the fundamental mode is the LP01 mode. So for L equal to 0, actually only one solution is present, because the cosine L theta term is just cosine of 0, so is equal to 1. So this is the function remaining. Otherwise, for sine, the sine of L theta for L equal to 0 is clearly sine of 0, which is 0. So this solution, the B solution, is not present when L is equal to 0. So this is the reason, because the fundamental LP01 mode is just one spatial orthogonal mode. This one. So So for LP, so any LP modes with L equal to 0 can be written as LP 0 and then a generic mu, because mu is an integer starting from 1. So mu, so we have LP01, LP02, etc. Okay. All the modes LP with 0 as the first index. In this case, if you write again the horizontal LP mode, we obtain clearly the radial function 0, L equals 0 mu. The azimuthal part is absent because it is simply, it is 1, it is independent of theta, but on theta. Beta, the beta is the propagation constant of this LP 0 mu mode. Okay, the interesting thing is that this function does not depend on theta. It means that the electrical field for all the L equal to 0 modes only this mode, this L equal to 0 mode, the field is circularly symmetric. So the field and also the intensity, which is the squared modulus of the field, is circularly symmetric in any transverse plane. So also the intensity pattern, the intensity contour map for L equal to 0 are circularly symmetric. Like the fundamental mode. It is well known that the fundamental mode is similar, from a topological point of view, is similar to a Gaussian. So the contour map, there is a central lobe, a central bright lobe, and a decreasing intensity toward the infinite in all the direction. So this is the LP01 mode. So the LP01 mode contain just one spatial configuration, only one. But there are two possibilities in terms of state of polarization. That is, the fundamental LP01 mode could be horizontally polarized, like in this case, or vertically polarized, which is the orthogonal polarization. And the vertical state, in the vertical state, the electrical field oscillates exactly along the y-axis. So the vertical state shows an x component exactly equal to 0, and on the other hand, the y component is like this. So this is the vertical mode. Yeah.
I don't understand what they're saying. Too fast and I cannot follow. So could you please slow down a bit, because actually from the moment you're starting to write on the board, I didn't get anything.
Okay. So have you understood the meaning of the horizontal LP mode. Okay. Okay, this is the optical fiber, the z-axis, and the transverse plane x and y coordinates. Okay. The horizontal, in the horizontally polarized LP modes, the electrical field oscillates exactly along x. Okay. In the vertically polarized LP mode, the electrical field oscillates exactly along the y-axis. So, the mathematical expression, the general mathematical expression for the vertically polarized and cosine kind of the azimuthal term, being vertical, it means that the horizontal component is 0. Okay, so you can interchange the position, but it's the same. So the x component is 0. On the other hand, the y component contains the field. So the y component has the general expression having the radial part by the azimuthal part and by the propagation, the propagation term, the phase propagation term. Also for the vertically polarized LP mode, you have two azimuthal possibility. That is the cosine kind, or otherwise the sine kind. The cosine and sine are different. Are always present. Are both present. Just for L, which is not 0, because in the case L equal to 0, you do not have cosine or sine. You just have 1 or 0, but 0 is not a mode. Okay. So this is the general expression. For solving the exercise, that is
one special.
You want to determine the intensity pattern in the transverse plane of the LP modes. So the general rule are, at first we have to distinguish the L equal to 0 case from the other cases. So for L equal to 0, we have a circularly symmetric pattern and the other condition is that the field is maximum on the axis. This is a topological property of this radial function with L equal to 0, because you have seen in the lesson that this field must satisfy the Helmholtz equation. That is for any component of the electrical field and the same for the other component. This is the Helmholtz equation. So the LP modes are obtained, these fields comes out from the solution of the Helmholtz equation. This is, you can also name K0, which is the K referred to the vacuum. So 2 pi divided the lambda in the vacuum. And this is the index of refraction, which is a radial function, a function of the radius. This is the general Helmholtz equation applied to the optical fiber. For obtaining this particular solution, you see that the solution is the product of different terms, and each term depends on just one coordinate. This is the radial part, depending just on rho. This is the azimuthal part, depending just on theta, and this is the axial part, depending just on z. When you factorize in this way the solution, like in LP mode, the radial function, this is just a reminder of the lesson, of the theory. I repeat, for solving the numerical exercise, it is sufficient to understand and to plot the intensity pattern. Okay, this is just a resume. So, if you substitute this general expression here by means of algebraic passages that you have seen in the lesson, in the slide, you will obtain this equation, this differential equation. So the second derivative with respect to rho of the radial function plus the inverse of the radius by the first derivative with respect to the radius of the radial function, and finally this term this is the azimuthal index L squared divided the square radius. This is a proportionality constant, cioè a proportionality factor multiplying the radial function. So the different radial function giving the different mode distribution are obtained solving this differential, second order differential equation. Clearly, the shape of the modes, the shape of this function depends on the shape of the index of refraction. So different kind of fiber show different radial function. But for the common fiber, the topological, the geometrical distribution of the field are all of the same kind. It changes just the exact shape of this radial function, but the zero, the nodal lines, etc. are the same. And for example, in the particular case of n constant, for example, if you consider the step index fiber, n, the index of refraction, as a function of rho, that is the distance from the axis of the fiber, has clearly this expression. This is A, that is the radius of the core. So for ρ less than A, the index of refraction is constant and has the high value of the index of core, but is constant. On the other hand, for ρ greater than A, that is in the cladding, the index of refraction is different, but is still constant with a different value, the index of the cladding. So for the step index, this is the step index fiber. For the step index fiber, we have to solve two different equations with the two different value, and then to match at the boundary between core and cladding, to matching the radial function. But the interesting thing is that if this n is a constant, this equation is exactly a Bessel equation. So this is the reason for having Bessel solution for the step index fiber. On the other hand, if this squared index is a parabola, has a parabolic shape, is a shape like this. So in the core, the solution of this radial equation gives the Lagergauss function. And then in presence of a finite cladding, you have to match the Lagergauss solution with the Henkel solution in the cladding. So the cladding, consider so for example, if you consider the fundamental, so the LP01 mode, we will obtain a Bessel or a Lagergaussian function which has a similar shape, bell-shaped, decreasing shape, but clearly with different number. But the topological characteristic is the same. So you have a Bessel, either a Bessel or a Lagergauss, matching a Henkel. In this case, you obtain J0, because for L equal to 0, you have to consider the J0, which is function of K ρ, but K is the Greek K depending on the indices, in this case 0, 1, and outside you will have the Henkel depending on the gamma parameter 0, 1, because it is corresponding to, for example, the LP01 mode by ρ. Okay, now we can count the different orthogonal mode in the different cases. Okay, so LP01 is this one. There are two orthogonal possibilities. The vertical, which means that the electrical field oscillate in the vertical direction, and the modal pattern is this circular symmetric spot. But we have also the LP01 horizontal, which is the same as a circularly symmetric intensity pattern, but the direction of the oscillation of the field is you can also is horizontal. And these two modes are, from a point of view, of a mathematical point of view, orthogonal. They are completely independent. So the LP01 corresponds to two orthogonal modes due to the two different polarization with the same pattern, the same spatial pattern. If we consider a greater mu, so in general, mu, the number mu minus 1 is the number of zeros not in the origin, that is not in the zero, because in the zero all this pattern with L equal to 0 have a maximum, but in general mu minus 1 is the number of zeros of the radial function. This is the general meaning of the radial index mu. For example, for LP01, mu is equal to 1, so mu minus 1 is 0. So there are no 0, so the pattern is decreasing. Is this condition? The radial function start from the maximum and then decrease, but we have no zeros. Now we consider the LP02 case. So the LP02 case, mu minus 1 is 1, okay? And actually, if you consider, if you remember from the slide of the Bessel function, the radial function for L equal to 0 but mu equal to 2, corresponding to LP02 mode, presents 1, 0. Okay? So the higher order modes presents a higher number of zeros. And which is the meaning in case of the LP02 mode for our intensity pattern? L is equal to 0, so it remains the circularly symmetric shape. But this 0, when you make a revolution around the z-axis, it means that the modal pattern of the LP02 present one nodal ring. This is a nodal ring. Nodal means that the field is 0. That is a ring in the transverse plane xy in which the field is exactly 0. Nodal is synonymous of 0 field. So I use the dashed line. So if you consider the intensity is the squared modulus of the field. So we consider the squared modulus of this radial function, which is in a field function, and the square of this function is this one. Okay. This position, which we name rho 0, is the distance correspond to this radius. That is, in the transverse plane, you will obtain on this circle with radius rho 0 corresponding to the first zero of the radial function, you will obtain a field and so an intensity exactly equal to 0. And knowing the node allows you for plotting the overall intensity pattern. The central region, okay, so the light is separated by the node. Another node is toward the infinity, is not at the infinity, but the successive zero is at the limit, at the infinite limit. So it means that if you consider this radial intensity distribution, for obtaining the transverse contour map, you can make a revolution around the z-axis. So this zone corresponds to the central lobe, which is circularly symmetric. And this relative maximum, which is beyond the zero, this relative maximum corresponds to a bright ring. Okay, so the LP02 intensity pattern is this one. A bright central spot surrounded by a bright ring. Between the ring, the bright ring corresponding to the maximum, and the central spot corresponding to this peak, there is the one nodal ring. One because mu is 2. Okay, so further on, it is clear that the LP03 mode, will present 2. Mu is equal to 3, so mu minus 1 is equal to 2. We will have two zeros, okay, 2 zeros, so 2 nodal rings. Between the first nodal ring and the second nodal ring, you will have this bright ring, and also between the second nodal ring and the infinite. So in the case of LP0 mu modes, you will have a central bright spot surrounded by mu minus 1 bright rings. Okay, but okay, the fundamental thing for all the L equal to 0 mode is that you have just 2 orthogonal modes corresponding to LP01, 2 modes corresponding to LP02, because you will have 2 choices, the horizontal possibility and the vertical possibility. But we will not have the choice between cosine or sine, because for L equal to 0, there is no azimuthal dependence. So you have to count DLP 0 mu modes like two possible orthogonal modes. So you have to remember this fundamental property of L equal to 0 modes. Okay, now we move to the L equal to 1 and etc. We start from the LP 1 and also with the mu equal to 1. This is the second mode. When L is equal or greater, you will have a particular condition, that is the RL, the radial function in 0, that is in the origin, is 0. So this is a different situation from the L equal to 0, a completely different situation. The reason, if you think to the step index fiber, so if you think to the Bessel solution, is that when L is equal to 0, when L is equal to 1, you have to consider the J1 function. And this is the argument depending on the Greek K. But clearly all the Bessel solution with L not 0, that is L equal to 1, 2, etc., present a 0 in the origin. Okay? So this is the reason, because the LP with L greater or equal or greater than 1 are 0 in the origin, for radius 0. Okay, in this case, the LP11 mode shows two possibilities, that is the horizontal polarization or the vertical polarization, and also two possibilities for the azimuthal term, either the cosine of theta, because L is equal to 1, so we have just cosine of theta, or sine of theta. So the total count of the orthogonal modes for the LP11 modes, and in general for any LP modes with L equal or greater than 1, will be 4. So the LP11 actually is not a single mode, but is a family of 4 orthogonal modes which are degenerate. Degenerate means that all these 4 modes shows the same beta, the same propagation constant, which is characterized only by the indices. In all these 4 modes shows the same propagation constant beta 1, 1. Now we want to plot the intensity pattern. So the general meaning of L is the number of nodal, in this case, not rings as in case of mu, but nodal lines. I not plot the axis, but I consider just this reference. For example, if this is okay, this is the reference and the origin, sorry. The cosine type, so the A type, A state for cosine type, the cosine type shows a vertical nodal lines, which is the reason. The reason is that the cosine of theta is equal to 0 for theta equal to plus or minus half pi. It's clear? So the cosine, this is the reference, the cosine of 90 degrees, that is the cosine of plus half pi, is 0. And also, this is exactly half pi, and also the cosine of minus half pi is 0. So, in the vertical line through the center, you will have a 0. And this is the cosine. We are considering LP11. So mu is 1, mu minus 1 is 0. So there are no other zeros in addition to this nodal line. So the pattern will be this one, will be two lobes separated by the nodal line. So this is the LP11, so-called A, corresponding to a cosine in the azimuthal term. On the other hand, I can obtain also the LP11B, which correspond to the sine term in the azimuthal term, but the sine of theta is 0 for theta equal to 0 or pi. So this is the origin. So the sine corresponds to an horizontal nodal line, and the field will have two maximum, two lobe, separated by the horizontal nodal line. Okay? And there are the two possibilities, the horizontal, the LP11B horizontal, or the LP11B vertically polarized. And the same for the LP11A, either horizontally polarized or vertically polarized. So the total count of orthogonal modes showing the same beta 1,1 propagation constant are 4. Okay, now we want to increase the mu. you increase the mu, LP1, 2, the number of nodal lines for each kind of mode is again 1. For example, vertical for A. But 2 means that you will have one nodal ring. So this is the origin. You have to plot a dashed line corresponding to a nodal ring. And the bright spot are in the region defined, delimited by the nodes. The vertical line of nodes and this ring of nodes of zero field. In the dashed line or in the dashed ring, the field is 0. And you will have two lobes like in LP11, but you will have these other two half moons, because these are 0. The successive 0 is not at the finite, but it is at the infinite. So between this finite 0 and the infinite, you will have a relative maximum. That is a bright zone. Okay, and also in this case, you will have the A type cosine, or the other the B type. The A could be horizontal or vertical, and also the B. So you will have 4 orthogonal degenerate LP1, 2 modes. Okay, so on, increasing the, but okay, you will not encounter great higher LP modes. Okay. The last thing is now to consider L equal to 2, for example. So L equal to 2 shows the two different azimuthal terms, cosine of 2 theta and sine of 2 theta. There are these two possibilities. This is the A possibility, and this other the B possibility. If you consider the cosine, so cosine of 2 theta will be equal to 0 for 2 times theta equal plus or minus half pi. So equivalently theta equal plus or minus 1/4 of pi. That is plus or minus 45 degrees. So the nodal lines are 2, because L is equal to 2, and L is the number of nodal lines. And are these two orthogonal lines. And if we consider LP to 1, so the minimum mu, the minimum mu 1 means that there are no nodal rings, and so the pattern is this one. Okay, this is LP21A. If you consider the LP21B, you can verify, but for the sign, the nodal line are 0, because the sign of 0 is 0, and also the vertical, because 2 times half pi is equal to pi, and the sign of pi is 0. So the LP11B is similar to LP21A, the B just by making a rotation. Sorry. Okay, these are obviously symmetric. Okay. In case of increasing the mu, considering a mu equal to 2 means that there will be one nodal ring. Okay. The total count of LP21 clearly is again 4, because any LP mode with L different from 0 shows 4 possibilities. Either A or B combined with either horizontal or vertical. If we consider LP22 mode, for example the A, the nodal line remains these two nodal lines, because L is equal to 2, and one nodal ring. So we will have a central region similar to LP21, that is these 4 main lobes. But then in the regions delimited by the nodal lines and the nodal ring, you will have a distribution with less absolute value of intensity, but a distribution like this. Okay. Yeah.
For LP21, those are horizontal or vertical or line?
LP21B. The nodal lengths are 2, both the horizontal and the vertical. Okay. Is the question? Is it the question? This circle. Okay. You will find the plot, the exact plot in the file, but you can imagine that the 0 the field is maximum far from zeros. So the right form is like this. But it is a numerical. You can plot. You can see the right. But for solving the exercise, it is sufficient to draw a bright spot in the right region. Okay. Okay. So we can answer to the last question of the exercise. So in the exercise, at lambda, at this lambda, using the cutoff table, you have obtained four LP family of modes, that is LP01, LP11, LP12, and LP02. Okay, now you are able to plot the intensity mode pattern. You can check on BIP, but very quickly, LP01 is this one, LP11, this is the A, and this other is the B, LP12, no, sorry, it was LP21. LP21, you have two nodal lines. This is the A case, and this is the B. And mu is equal to 1, so no rings, no nodal rings. Okay, and LP02, 0 means asymmetrical pattern with the bright spot in the center, surrounded by 2 minus 1, just one nodal ring. So you have also a bright ring. Okay. So for solving the exercise. And the last question was the total number of orthogonal modes propagating at this lambda, which is the total number. LP01, because L is equal to 0, we do not have the two A and B types, but just one symmetric solution with the possibility of either horizontal or vertical polarization. So the LP01 family or subgroup of mode correspond to two modes, and also the LP02, because L is equal to 0, mu is not interesting for the count of total number. So also in this case, you will have two modes, the horizontal or the vertical. But in these other two cases, L is different from 0. L is equal to 1 or L is equal to 2. So there are two kinds of azimuthal distribution, and for any kind, there are also the two possibilities, horizontal or vertical. So very simply, the total number corresponding to this subgroup is 4, two azimuthal possibility by two polarization possibilities, and also in this case is 4. So the total number is 12. Okay. Okay, now we skip the third, the B3 exercise. It is a very simple exercise. You can solve. You can find the text on BIP and also the solution. But now we solve the fourth exercise related to a graded index fiber. Is it clear this? Okay, in this case, we consider not a step index, but we consider a graded index, optical fiber, and in particular with the so-called parabolic core, and we consider also a finite cladding surrounding. So, and we consider with an index n0. N0 is the index of refraction on the axis, exactly at the center of the fiber. And this N0 is 1.463, and the index of the cladding is equal to 1.46. So it means that the behavior of this fiber in terms of index of refraction as a function of rho, that is the radial distance between the axes, is this one. So when the radius is greater than a, we have a constant index, the cladding index. In this case, this value. But in the core region, that is for radius less than a, this is the core, you will have a parabolic distribution. For precision, it is the squared n, not the n, the square, which is a parabola. But in abbreviated term, parabolic core means that the square of the index is a parabola, not the index. And when the squared index of refraction is a parabola, it is a quadratic term, so the solution in the core is a Laguerre-Gaussian solution. It is a particular graded index for having Laguerre-Gaussian solution, as you have seen in the theory, in the lessons. And this n0 is the maximum value, so it is in the correspondence of rho equal to 0, just on the axis. Okay, for this, so we have defined all the parameters of the fiber except the radius. So in this problem, we want to calculate the radius of the core, A, for having single mode propagation exactly in the range lambda greater than 1200. Okay, this is a typical condition because in this case, in the second and in the third windows, this fiber will be a monomode fiber, that is a single mode propagation. So So we know the range of single mode propagation, and we want to obtain the radius. And the last question is which guided LP modes can propagate at lambda. For example, in the first window, the center of the first window is around 810 nanometer. This is a lambda, not the center, this is a lambda in the first window. And also plot the transverse intensity patterns and count the total number of the orthogonal guided modes propagating at this wavelength. Okay, you have the solution. Now I move quickly to the solution, but you have the complete solution on BIP. Okay, but the fundamental thing is to use the V parameter. The key is the V parameter, or normalized frequency. So the V parameter is proportional to a frequency, so is inversely proportional to a lambda. 2 pi divided by lambda is the k in the vacuum, by the radius, by the numerical aperture. But we have to define the numerical aperture. In this parabolic graded index, the numerical aperture consider, instead of the constant core index like in step index, consider the peak value of the index on the axis. So the numerical aperture is the square root of the square of n0 minus the square of n clamping. So it's very similar to the step index case. Instead of n core, you have to consider n0. So we are in the typical weak guidance condition. So the variation is very little, and also the numerical aperture will be small. And this is the value of the order of 0.1. Okay. Now we have to consider this data. We remember that the single mode condition is that the V parameter must be equal or less than the cutoff V of the second mode, that is the cutoff of the LP11. Because in this case, just LP01 mode will propagate, because LP11 is not present if this condition is satisfied. And if the second mode is not present, also the third, the fourth, etc. modes are not present. So just the fundamental. but the cutoff V of the LP11 mode is no more the cutoff for the step index, clearly, but so it is not 2.405, which is the cutoff for the step index considering Bessel solution. In this case, we have a parabolic graded index corresponding to Laguerre-Gauss solution, and from a numerical consideration, the cutoff is different. And you have to remember this number also. You have to remember 3.51. But this condition we have so this is the V. I demonstrated for the step index case that this condition, this single mode condition, correspond in terms of lambda, and V and lambda are inversely related, correspond to lambda. In terms of lambda, to lambda, I have to invert the direction of this equation. So lambda is greater or equal at limit to the cutoff lambda of the LP11 mode. So this is the single mode condition in terms of V, or equivalently in terms of lambda. So if you compare this condition with this data, immediately you see that the cutoff lambda is this one. So, sorry, nanometer clearly. So the cutoff lambda of the LP11 mode is exactly 1,200 nanometers. Okay, now knowing the cutoff lambda and knowing this cutoff, we can obtain the radius. So, from the general expression of the V, you have to make two substitutions. Instead of V, you have to consider the cutoff V, that is this number. And correspondingly, instead of lambda, you have to consider the cutoff lambda, that is the data. So the relation, the right relation is the V cutoff is equal to 2 pi divided by the lambda cutoff A by the numerical aperture. So A is V cutoff 1,1, okay, 1,1. So A is V cutoff by lambda cutoff divided 2 pi by numerical aperture. I will substitute the V cutoff, which is this one, by the lambda. I can express the lambda in nanometers, in micron. It is 1.2 microns divided 2 pi by the numerical aperture was 0.0936. Okay, nanometer. So the result is 7.2 microns. So this is the radius for having this cutoff lambda for the LP11 mode. Okay, now we move in first window, that is at lambda 810. And for calculating the V at this lambda, because for obtaining the number of modes propagating at this lambda, clearly you have to evaluate V at the lambda of interest, because the V is not absolute, just the cutoff are absolute. The V value depends on lambda. So you can micron, 0.81 micron and you consider the previously calculated radius. So the result will be clearly greater than the cutoff, because the lambda 810 nanometers is lower. You can also use this expression, exploiting the inverse proportionality between V and lambda. You can express V at this wavelength as the difference between the reference wavelength divided by this wavelength, multiplying the V at the reference wavelength. But this reference wavelength was the cutoff. So we'll obtain simply the cutoff, the V cutoff multiplied, enhanced by this ratio, because reducing the wavelength with respect to the cutoff makes the fiber multimode, that is, the V is greater than the cutoff. Okay. So this is the V, which must be compared with the cutoff table. Okay, for solving the exercise, the cutoff table will be given, but the cutoff table for the graded parabolic index is different than for step index. So L